had an initial stint with Combinatorics, basic principles of counting, looked into some very, very basic simple problems, simple applications, and that is all that is there actually. So there is no complexity in this business of counting. There would obviously be some sophistication that we'll add to make life easy for you. But even with the simple little things that we have learned so far, we've actually graduated to a level where we can, incorporate sophistication in our own working, our own way. So the next bunch of problems that I'm going to deal with in this sheet titled Combinatorics Sticking to Basics, we'll just breed a little more maturity, little more familiarity with fundamentals related to counting. All right. So let's then start examining these problems of the sheet titled Combinatorics Sticking to Basics. The first problem of the sheet is about a structure of this kind. In which there are 3 rows. Row 1, R1, has 2 cells in it. Row 2, R2, has 2 cells in it. This is the third row, R3, and this has 4 cells in it. Right? Now, what is it that we want to do with the 3 rows? We have a word called person. We want to place these letters, P-E-R-S-O-N, these 6 letters, in 6 cells here, I want to select 6 cells in this array of cells, and obviously you can see there are 8 cells, but I want to select 6 of them, where I could accommodate the letters of this word person. But I want to make sure that in organizing these letters in these cells, there is no row which is empty. Each row has at least one element in it. At least one cell of every row must be occupied. Question is, in how many ways can I do that? So, break the problem into 2 parts. First, select 6 cells from here, commensurate with the condition. Select 6 cells out of 8, commensurate with the condition that every row must have at least one cell occupied. Right? There are a certain number of ways in which you could select 6 cells. We'll find that number. All right. And then in these 6 cells, I'll arrange these 6 letters. In each choice of 6 cells, the 6 letters can be arranged in 6 factorial ways. Right? So what is the whole problem all about? Find the number of ways in which 6 cells could be selected, keeping in mind that every row has at least one cell selected. Second, then the choice of 6 cells would cause the 6 letters to be arranged in those 6 cells in 6 factorial ways. Clear about the proposition, right? Okay. Now, these are the various things that we could do. Row 1, R1, row 2, R2, row 3, R3. There are 3 rows, right? I want to select 6 cells with at least one cell in each row. One possibility is, from row 1, I select 1 cell. From row 2, I select 1 cell. And from row 3, I select 3 cells. Yes or no? That's one possibility. Sorry, 4 cells, 6 cells, 4 cells. That's one possibility. Or I select 2 cells from here, I select 2 cells from here, and I select 2 cells from row 3. That's another possibility, right? Or the third possibility is I select 2 cells, 1 cell and 3 cells. And the last possibility is 1 cell, 2 cells and 3 cells. Yes or no? These are the 4 distinct possibilities, independent possibilities which I can explore. Right. So now let me see, find the number of ways in which this choice could be created. Number of ways in which I could execute this choice. One cell from row 1 and 1 cell from row 2 and 4 cells from row 3. Okay, let me find out the number of ways in which each of these combinations could be executed. Ways to execute. Okay. One cell from row 1 can be selected in 2 ways, right? Then one cell from row 2 could be selected in 2 ways. Any one of the 2 cells could be selected. And the 4 cells from row 3 could be selected only in 1 way. 1 way. So that makes it 4 ways of executing this combination. 4 ways of executing this combination. Okay. 2 cells from row 1. In how many ways can? 1 way. 2 cells from row 2. 1 way. 2 cells from row 3. 1 way. Yes or no? Oh, I'm sorry. 4C2 ways. 4C2 ways. Yes or no? There are 4 cells. I need to select 2. I can do so in 4C2. 4C2 is 6. So that makes it 6 possibilities for this. Yes or no? Now, 2 cells from row 1. 1 way. 1 cell from row 2. 2 ways. And 3 cells from row 3. 4C3. 4C3. Yes or no? 4C3 ways. 4C3 is 4. 4C3 is 4. So that makes it 8 ways. Okay. Then again, 1 cell from row 4, 2 ways. 2 cells from row 2, 1 way. And 3 cells from row 3, again 4C3. That makes it 8 ways in all. Right? So the total number of ways in which I could select 6 cells, given the condition that every row has at least 1 cell which is active, there's 4 plus 6, 10 and 16, 26. 26 ways of selecting 6 cells? Yes or no? 26 ways of selecting 6 cells? You have selected 6 cells in 26 ways. Then each way of selecting 6 cells can be populated by these letters in 6 factorial ways. Yes or no? 26 ways of selecting 6 cells, and each of these modes would correspond to 6 factorial ways of organizing these letters. 1 letter per cell. 1 letter per cell. 6 factorial. So 26 into 6 factorial, whatever turns out to be is the answer. Right? How much does it turn out to be? 18? 18,720. Okay. Okay. So far so good. Yes or no? Do you all understand everything that I have communicated here? Right? Let's go ahead, examine more. Can I wipe this off? Can I wipe this off? Okay. Number 2. We want to find the number of ordered pairs x comma y. We want to find the number of ordered pairs x comma y such that x and y are positive integers, means natural numbers. X and y ought to be natural numbers. X and y are natural numbers such that x plus y less than or equal to 4. All possible ordered pairs x and y in natural numbers such that x plus y is less than or equal to 4. Now, one thing which I want to take you back to, straight out of the previous class, this recipe where the number of natural number solutions to this equation, xi's are all natural numbers. Do you remember this? N minus 1, see? R minus 1 is the number of natural number solutions to this equation. Right? Number of whole number solutions to this equation was n plus r minus 1 c r minus 1. Recall that? Okay. Now this is a little bit of an extension of the same idea, the problem at hand. What I do is, see, that's again a basic tenet of mathematics. You convert a problem into a known problem. Into a known problem. Smaller or bigger does not matter. You convert a problem into a known problem. Now, how do I convert this problem into a known problem, given that x and y are natural numbers? Now, let me convert this inequality first into an equality. Yes or no? Let me first convert this inequality into a equality. How I do that is as follows. I say x plus y is 4 minus z, where z is greater than or equal to 0. Yes or no? Then x plus y will be. And of course, do you realize that? Right? Now, that means z is a whole number, but x and y are natural numbers. In this case, z is a whole number, but x plus y are natural numbers. So what I do is, I want this entity, which is right now a whole number, to become a natural number. So how do I convert a whole number into a natural number? I add 1. I add 1, right? So I perform the following manipulation. X plus y plus z plus 1 equal to 5. How about it? Now z plus 1 is a natural number. And see, the number of solutions to this will be the same as number of solutions to this. Yes or no? The number of solutions to this equality will be the same as the number of solutions to this inequality. Yes or no? Now, I can then write this as x plus y plus, say, z prime equal to 5. Where now x, y and z prime are all natural numbers. So the number of natural number solutions to this equation will give me the number of ordered pairs x comma y that will be commensurate with this inequality. Yes or no? And the number of natural number solutions to this equation is n minus 1 c r. R is 3 here, right? So 5 minus 1 c, r is 3, 3 minus 1, which is 4c2. That is 6 ways. That is 6 ways. Yes or no? If you have performed trials and arrived at 6, you would know. See, since this was a small number, you could have taken cases like x plus y equal to 1, x plus y equal to 2, x plus y equal to 3, and x plus y equal to 4. You could have found the number of natural number solutions to each of those 4 cases. But if this was a very big number, then you're not going to get into the audacity of, dealing with every case. Rather, you would intelligently convert the problem to a known smarter problem. All right? And this is what you do. So this is not just about dealing with this problem, it's a basic tenet of mathematics. When you solve more problems, why do you become more accomplished with problem solving? Because then there is greater database into your head. And now every other problem that you encounter, there is an internal pointer which seeks a similarity with a known situation in your database. It tries to connect with that. That's how the heuristics works inside. That's the way the mechanism of problem solving works inside you, right? And that's why, when you're solving more problems, you're becoming a smarter problem solver. That's how it happens. Okay, shall we then proceed to the next problem? Problem number 3. So there are 3 girls and 9 boys, and there are 2 vans, one with a front seat, back seat, front seat, back seat. There are these 2 vans, front seat, back seat, right? 3 in the front. There are 3 seats in the front, and there are 4 seats at the back. There are 4 seats at the back. All right. Now, you want to accommodate these 12 people. In these 12 people would have to be accommodated in these 2 vans, given that the girls will always occupy the back seat and will always be together. That means, if these are 4 slots, for example, in this van, the 3 girls could be placed in 2 ways. The 2 ways of selecting 3 slots could be 1, 2, 3 or 2, 3, 4. And then the 3 girls in a given selection of 3 slots could be permuted in 3 factorial ways, right? So first you will select 3 slots for the 3 girls. 1, 2, 3, that's one way. 1, 2, 3, that's another way. In each van, the 3 slots could be selected for the girls to be seated together, could be either first, second, third or second, third, fourth. 2 ways, right? Now, each time you have selected 3 slots. In those 3 slots, the 3 girls could be accommodated in 3 factorial ways. But the same thing could have been done to this van. The girls could have been accommodated in these many ways in this van or this van. That means that doubles the number of cases in which the girls could be accommodated. Yes or no? For this van, 2 into 3 factorial ways, and for this van, 2 into 3 factorial ways. So the total number is 2 into 2 into 3 factorial. That's how the girls could be accommodated. Now, there are 14 slots in all. 3 have been occupied by girls. How many are left? 11 slots. In the 11 slots, I want to arrange the 9 boys. And the order is important. So that's going to be 11P9. 11P9. Yes or no? So that turns out to be 11 factorial, 6 2s are 12. So that makes it 12 factorial, because there is a 2 factorial here that will get cancelled with this. And this is 2 into 6, 12 into 11 factorial. 12 into 11 factorial will be 12 factorial. 12 factorial number of ways. Yes or no? Right? Got me, no? Number 4. There are 10 students in a class. Three girls and 7 boys. And I want to arrange them in a row such that no 2 of the 3 girls are consecutive. No 2 of the 3, same idea. In this case, first I deal with the 7 boys. The 7 boys can be arranged in how many ways? 7 factorial now, because they are different. Right? Now because they are different. Right? So the 7 boys can be arranged in a line in 7 factorial ways. The order is important. Now that leaves you with how many spaces? 6 into 8 spaces. 1 space, 2 space, 3, 4, 5, 6, 7, 8. 8 spaces. Now in these 8 spaces, what do you want to do? You want to arrange the 3 girls. You want to arrange the 3 girls. In how many ways can you do that? 8p3 precisely into 8p3. 8p3 ways. 7 factorial ways in which the guys could be arranged. And it leaves me with 8 spaces to accommodate the girls, given the condition that no 2 girls would be consecutive, right? If the girls are placed where these arrows are, then no 2 girls would be consecutive, and the mission accomplished, right? So in these many ways. Fairly simple, isn't it? Number 5. There are 6 pluses available to you. 6 pluses available to you. And there are 4 minuses available to you. Oh, I have missed out question number 4. Okay, let me finish 5. I'll come back to 4. How does it matter, right? The 5th problem, there are 6 pluses and there are 4 minuses. And you want to organize these along a line. And in such a way that no 2 minus signs come together. no two minus signs are next to each other, right? Every minus sign should be separated from its nearest minus sign with at least one plus sign. That's what you want, right? So what you do is, first of all, just think of the 6 plus signs. The 6 plus signs, in how many ways can you arrange them along? But one way, one way only. The 6, they are all identical. Like I said, there are times you should unlearn what you have learned. Be like a child in order that you count well. If I ask this question to a small little kid, he would have said 1. Because, you know, he didn't learn permutation combination in my class. There are 6 pluses to be arranged in a row in only one way. Yes or no? Right? So, okay, first of all, I arrange the 6 pluses. 6 pluses. Right? There is only one way of doing that. And then, let me find out the number of ways in which the minuses could be arranged. Now, these 6 pluses leave me with 1, 2, 3, 4, 5. And at the 2 extremes, 2 more. 7 spaces in which the minus signs could be placed, isn't it? If the minus signs are placed here, 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 in these 7 slots, then the no two minus signs will be together. Yes or no? So the out of these 7, how many do I want to select? 4. Where I could accommodate the minus signs, right? So one way of arranging the pluses, and then just select the 4 slots from 7 available. 3, 4, 5, 6, 7. You want to select 4 of these spots in which the minus signs could be arranged. Once you have selected the 4 slots where you are going to place the minus signs, now you take the minus signs and arrange them in these 4 spots. In how many ways can you do that? One way, yeah. Right? So 7C4, which is 7 factorial by 3 factorial into 4 factorial, 7 into 6 into 5 by 6, that is 35 ways, right? 35 ways of accomplishing the mission. Got me? Number 4. Can I wipe this off? Number 6. Number 6 is about a staircase of 2n steps. Number 6 is about a staircase of 2n steps. Staircase of 2n steps. All right. Now, there is this gentleman who wants to climb the staircase. What he does is, he takes steps in unit of 1s and 2s. Either he climbs 1 stair at a time or he climbs 2 stairs at a time, right? So, I'll call the 2 stair at a time as a double step and a single step, right? He takes a double step. He's capable of taking a double step. Means 2 steps in one shot, 2 steps in a shot, or he could take a single step. Means 1 step at a time. Right? A double step or a single step to climb 2n steps in all. Clear? Now the question is, in how many ways can he do that? In how many ways can he do that? What we do is, let us say that R be the number of double steps that he takes. R is the number of double steps taken. R can be 0, R can be 1, R can be 2, R can be 3, or R can be n. Because when R is n, all the 2n steps are covered. All the steps he's taking are double steps, and 2n steps can be covered in n units. Yes or no? So R could be an integer lying between 0 and n. R could be 0, 1, 2, 3 up to n. N plus 1 possibilities for R. If r is 0, that means all the steps that he is taking are single steps. If r is n, that means all the steps that he is taking are double steps. Now, if r in general, so I'll have to sum up all cases. Whatever I find for a general r, I will have to sum up all the cases starting with r equal to 0 to r equal to n. I'll have to perform a count for r equal to 0. Then I'll have to perform a count for r equal to 1. Then for r equal to 2, r equal to 3, r equal to n, and I'll then perform a conventional summation on all these cases. Right? Okay. Now, if r be the number of double steps taken, then the number of steps covered is 2r in the process. If r double steps, each double step would be 2 steps. So r double steps means he would have covered 2r steps and all. Yes or no? Now, steps remaining. Is how many? 2n minus 2r steps remaining. Two n minus 2r steps remaining, yes or no? Now, how many single steps? 2n minus 2r single steps and r double steps. Essentially, 2n minus 2r single steps. These many steps remain, and they have to be covered in single steps. So if these many steps remain, that means 2n minus 2r single steps is what he takes. 2n minus 2r single steps is what he takes, and r double steps. These are the total number. Yes or no? If r be the number of double steps, that means the number of stairs covered in double steps is 2r. How many steps remain in all? 2n minus 2r steps remain, right? And they have to be in single units. So these many number of single steps, yes or no? These many single steps, right? These many single steps and r double steps. Do you understand the total number of units of steps? Total number of units of steps will be 2n minus 2r plus r. That's a total number of steps that he has taken. These many double steps and these many single steps. These many double steps are double steps and 2n minus 2r single steps. Yes or no? So total number of steps taken is 2n minus 2r plus r, which is 2n minus r steps is what he has to select. That means some of them would be double steps, r double steps, and 2n minus r single steps. Yes or no? 2n minus r steps in all. 2n minus r steps in all. Yes or no? Out of these 2n minus r steps, so that means actually for any given r, there will be 2n minus r steps in all that he takes. And out of these 2n minus r, he has to select r steps that are double steps. Yes or no? Out of these 2n minus r steps, he has to select essentially r steps that are double steps. Then the rest would be automatically single steps. Right? So in the whole problem then boils down to is if these are the total number of steps for any given r, and from there he has to select r steps. In how many ways can he do that? 2n minus r, c, r ways. 2n minus r, c, r ways. These are the total number of steps to be taken. And out of these many steps, there are r of them that are double steps. Question is, in how many ways can he select r steps from these many available? 2n minus r, c, r ways. So, 2n for a given r, this is the number of ways he can cover 2n steps in all, right? But r could have been 0, r could have been 1, r could have been 2, r could have been n. So the total count would be sum of all these cases for r equal to 0 all the way to n. So the required count is this, r equal to 0 all the way to n. That's the summation. Yes or no? Right? X, Y, Z are positive integers. X, Y, Z are positive integers means they are natural numbers. They can assume values like 1, 2, 3, etc. Such that X, Y, Z is 120. Such that X, Y, Z is 120. There are many combinations of X, Y, Z in natural numbers that will satisfy this equation. I need to find how many ordered triplets in X, Y, Z exist in natural numbers commensurate with this condition. Number of natural number solutions to this product equation. That's what we want to find. Now, actually a very simple problem. What you need to do is this 120 can be written as 8 into 15. 8 into 15 means 2 cubed into 3 into 5. Yes or no? That's resolving it into prime factors. Resolving it into prime factors. This is the only way you could do that. Now, look, what I'll start to do is each of these factors I'll start to assign to X, Y, Z. Now, and the number of ways in which I could assign these three factors to X, Y, Z will be the required number of solutions, yes or no? The number of ways in which I can assign these factors to X, Y, Z would be the number of solutions. For example, 3 could have been given to X or Y or Z. So there are 3 ways of dealing with this 3, yes or no? 5 could have been assigned to X, Y or Z. So how many ways of dealing with 5? 3 ways. Now, 2 cubed. We need to figure out how 2 cubed could be assigned to X, Y, Z. See, 2 cubed, for example, one way to write 2 cubed is 2 cubed itself. Now, 2 cubed all by itself bodily could have been given to X, Y or Z. So, one way to give 2 cubed, distribute 2 cubed to X, Y, Z is 3 ways. Either to X or to Y or to Z. Or I could have written 2 cubed as 2 squared into 2 into 1. Yes or no? 2 squared, 2 and 1. Now these 3 could be permuted amongst X, Y, Z in how many ways? 3 factorial ways. 3 factorial ways. Yes or no? 2 squared, 2 and 1 could be permuted amongst X, Y, Z in 3 factorial ways. 2 squared given to this, 2 to this, 1 to this, or 1 to this, 2 squared to this, 2 to this. That total count will turn out to be 3 factorial. There are these 3 entities to be placed in these 3 spots in 3 factorial ways, right? 6 ways. And then, what else? 2 into 2 into 2. In how many ways can 2 and 2 and 2 be given? Only one way. Only one way. Right? Now, that means 2 cubed could be disseminated to amongst X, Y, Z in 3 plus 6 plus 1, 10 ways. Either this could be a mode of distribution. 2 cubed given to each one of them, 3 ways. Given to one of them in 3 ways. Or 2 squared, 2 and 1 distributed in this product in 3 factorial ways, or 2, 2 and 2. Each one of them is 2. That can be done in only one way. So there are 10 ways in all. But that means 3 ways of assigning this, 3 ways of assigning this, and the number of ways of assigning 2 cubed is 10. So that makes it 90 ways in all. So there are 90 solutions in natural numbers to this equation. What I want you to examine independently, not right now, is if I said, all right, X, Y, Z are all greater than 1. Number of solutions in natural numbers provided X, Y, Z are all greater than 1. This includes cases where X, Y, Z could be 1, for example, right? So if X, Y, Z could be 1 onwards, including 1, then the number of natural number solutions to this would be 90 ways, 90 ways. Right? let's look at the next one. Simple, isn't it? How many 3-digit numbers have at least one even digit? 8. We are seeking at 3-digit numbers, units, tens and hundreds. We are seeking all 3-digit numbers, and we want at least one of the 3 digits to be an even digit. So first of all, unconditionally, how many 3-digit numbers in all are possible? 3-digit unconditionally. Obviously, simple to see. 9 ways you could have this, 10 ways and 10 ways. That makes it 900 3-digit numbers in all. I hope all of you understand this, right? This could be any number from 1 to 9, and this could be from 0 to 9, this could be from 0 to 9. Isn't it? 9 ways of assigning this part, 10 and 10 ways of assigning units and tens place. So that makes it 900 3-digit numbers in all, right? Now, see, if you look at the digits, 0, 2, 4, 6, 8. These are, let's say, the even digits. The odd digits are 1, 3, 5, 7, 9. Now, how many odd digits are there? 5 odd digits? It belongs to the category 2k, therefore even. 0 is of the type 2k, where k is 0, is therefore looked upon as even, right? In its formation, essentially. Now, what I do is, from this 900, I remove all those numbers in which digits are all odd. From this 900, total number of 3-digit numbers, I remove all numbers in which digits are all odd. Then the rest of the numbers will contain at least one even digit. Yes or no? So now if I have to construct a 3-digit number with all odd digits, then the hundreds place could be filled up in 5 ways, the units place, tens place in 5 ways, the units place in 5 ways. That makes it 125 numbers with all digits, 125 numbers with all digits odd, constituted out of this set, with all digits odd. These are the total number, and these are number of numbers with all digits odd. That means the rest of the numbers will contain at least one even digit. So the rest, which is 900 minus 125, which is 775 numbers, 3-digit numbers, will have at least one even digit. It will have at least one even digit. Yes or no? Number 9. N is a natural number greater than 1, say. And every n can be written as product of powers of primes, p1 to power alpha 1, p2 to power alpha 2, p3 to power alpha 3, pk to power alpha k. Every natural number could be resolved into factors of this kind. Now, what I want to do is, I want to break n as product of two natural numbers x and y. I want to break n as a product of two natural numbers x and y, such that x and y are relatively prime, isn't it? That means their HCF is 1, isn't it? When are x and y co-prime or relatively prime? If their HCF is 1, right? So now I don't want, that means I don't want x and y to have any factor other than 1 in common. I don't want x and y to have any factor other than 1 in common, right? This is what I want to do to n. Now the question is, in how many ways can I fragment n as a product x into y? Not the ordered pair. I mean, x into y and x are the same. You know what I'm saying? Such that x and y have their GCD equal to 1, right? Now, a fairly simple problem actually, except for its initial looks, which might be suggestive otherwise. See, I start with a slot for x, and you know, whenever I fill up slots, I'm building order in it. But I'll curb that order. I'll suppress that order in the end. First, let me look at the number of ordered pairs x and y that I can select. So these are my entities, p1 to power alpha 1, p2 to power alpha 2, p3 to power alpha 3, pk to power alpha k. Now realize that, suppose this was p1 cubed. Then p1 cubed would either go exclusively to x or will go exclusively to y. Because otherwise, if this was p1 cubed and this was p1 and this one p1 squared, then they would have a factor p1 common, which is not what we want. Right? That means these factors would go en masse to either x or to y. These factors would go en masse without getting fragmented either to x or to y. Yes or no? You know what I'm saying? No? You're not sure about this? Sure, na? Okay. That means the number of ways of delegating this to two spaces is how many? Two ways? Two ways of, so now I'm building order in it first, right? Two ways of delegating p1 to power alpha 1. How many ways of delegating p2 to power alpha 2? Two ways. It could either go to this place or to this place. Two ways. Two ways of p3 to power alpha 3. And two ways of p, so that makes it 2 to power k. But there is duplication of count here, because if xy has appeared in the count, then yx has also appeared in the count. But I would look upon them as the same. You know what I'm saying? I would look upon them as the same. So 2 to power k actually gives me double the required count. 2 to power k actually gives me double the required count. So the actual count would be 2 to power k divided by 2 if it's not ordered xy. Right? Because I'm only breaking it up into two factors. The order in which these factors are appearing is inconsequential. But this mode of counting has actually built order. I don't want that to happen. So I divide by 2 to suppress the order. You're not very sure about this, right? Achha, okay. Suppose, let me look at a simple case of this kind. Suppose I have 2 cubed into 3 squared. And I want to fill up these two spaces. X and y. 2 cube can go here. There are two ways of delegating 2 cube. Or 2 cube could go there. Yes or no? 3 squared either could come here or could go there. Yes or no? This is the number of ways in which I could break 2 cubed into 3 squared as a product of two numbers where their GCD is 1. But do you realize in the process of filling up the first space, filling up 2 cubed in 2 ways and 3 squared in 2 ways, I'm actually getting the same pair. So do you realize I'm getting double the count when I fill up these spaces? But the actual count is only 1. 2 cubed and 3 squared, and 3 squared and 2 cubed is the same pair of numbers whose GCD is 1. So actually it's going to be divided by 2. So the moment I fill up these spaces, I'm duplicating the count here. I'm doubling the required count. Therefore I divide by 2 to suppress that count. So 2 to the power k again has duplication of count, double the required count. Yes or no? If AB has appeared as a member in that count, then BA has also appeared as a member in that count. But those two should be required as 1. So I pair them up, divide by 2, and there we go. So the required count is going to be 2 to the power k divided by 2 unordered pairs is 2 to the power k minus 1. If somebody said, no, I want the ordered pairs, then that's 2 to the power k. Got me? Problem number 10. So there are 20 people and you want to organize them in 3 rooms. There are 20 people, you want to organize them in 3 rooms such that no room is vacant, right? These are the 20 people. these are the 20 people, and these are the 3 rooms. Three rooms. Right? And you want to organize these 20 people in the 3 rooms such that no room remains vacant. Such that no room remains vacant. In a given room, there must be at least one person. In a given room, there must be at least one person. Question is, in how many ways can I do that? Now, if there was no condition, unconditionally, the number of ways in which 20 people could be arranged is how much? Right. Each person could be accommodated in any one of the 3 rooms. So there are 3 ways of dealing with P1. There are 3 ways of dealing with P2. There are 3 ways of dealing with P3. And there are 3 ways of dealing with P20 if there was no condition. P1 could go to any one of the 3 rooms. P2 any one of the 3 rooms. P20 to any one of the 3 rooms. That means this is 3 to the power 20. Now, number of ways, suppose NR1 represents number of ways in which R1 remains empty. Number of ways in which R1 remains vacant, for example. That means now P1 could go to any one of the 2 rooms. There are 2 ways of delegating P1, 2 ways of distributing P2, 2 ways P3, 2 ways, right? So that makes it 2 to the power 20, yes or no? Yes or no? And this must be the same as n R2, number of ways in which R2 remains vacant. This is the same as the number of ways in which R3 remains vacant, yes or no? Now, number of ways in which R1 and R2 remain vacant. In how many ways will R1 and R2 remain vacant? Only one way, yaar. Absolutely. Think simple, yaar. If R1 and R2 remain vacant, that means all 20 people are dumped here to starve and to die to death. Right? Yes or no? So there is only one way in which R1 and R2 remain empty. R1. There is only one way in which R2 and R3 remain empty. There is only one way in which R3 and R1 remain empty. Yes or no? Yes or no? Now, number of ways in which R1 and R2 and R3 remain empty. 0 यार, ये कहाँ पे इसको हवा में लटकाओगे क्या ये लोग को? फुटपाथ पे थोड़ी भेजोगे? That option is not given, right? So number of ways in which R1 and R2 and R3, all 3 remain empty is 0. We are not allowing that to happen, right? Got me? Now, number of ways in which R1 or R2 or R3 remain empty, isn't it? This would mean number of ways in which R1 or R2 or R3 remain empty. From principle of inclusion and exclusion is summation NR1 minus summation N R1 and R2 plus summation N R1 and R2 and R3. Yes or no? What? Principle of inclusion exclusion? Isn't it? Now, in this case, this is NR1 plus NR2 plus NR3, which is, and each of them is 2 to the power 20. Right? There are 3 terms here, NR1, NR2, NR3, and each of them is 2 to the power 20. So, the summation NR1, this summation NR1, 3 into 3 into 2 to the power 20. Right. Now, this is 1 and 2, 2 and 3, 3 and 1, 3 members in this summation. Each of them is equal to 1. So minus 3 plus 0. This will give me what? This will give me the number of ways in which one or more room is empty, isn't it? This will give me number of ways in which one or more room is empty. Right? Number of ways in which one or more room is empty. And the total number of ways without a condition is how much? 3 to the power 20. And out of this 3 to the power 20, these are the number of ways in which one or more room is empty. That means from this, if I remove these cases, then I'll get the number of ways in which no room is empty. Yes or no? These are the number of ways in which one or more room is empty. Right, Ayush? These are the total number of ways. 3 to the power 20, right? So from this, if I remove those cases in which one or more room is empty, I get those cases in which no room is empty. So from the total, I remove the case in which one or more room is empty. I'll get the number of cases in which no room is empty. This is the required count. Yes or no? Got me? Right, direct application of principle of inclusion exclusion, right, Chirayu? Have I given to you in my last class the total number of factors of a given number? Alpha 1 plus 1 into alpha 2 plus 1 into alpha k plus 1, right? Total number of factors including 1 and the number itself. Have I shared that with you? We want to find the number of natural numbers n. We want to find the number of natural numbers n. The number of natural numbers n such that n is a divisor of at least one of them or 20 to the power 30. We want to find the number of natural numbers n which are divisors of at least one of these two numbers, which are divisors of at least one of these two numbers. So let me call this number a, 10 to the power 40. 10 to the power 40. This is 2 into 5. So 2 to the power 40 into 5 to the power 40. All right. Now, number of divisors of A is Na. How much? 41 into 41, isn't it? Right? 41 into 41, how much is it? 1681. These are the number of divisors of A. Number of, now the other number B is 20 to the power 30. So this is 2 squared into 5 whole to the power 30, which is 2 to the power 60 into 5 to the power 30. Now how many divisors of B? Right. 31 into 61. Right. How much is it? 1891. Okay. Number of divisors of B. Now, tell me this. What is, suppose C is the GCD of A and B. Right. The GCD of these two numbers is going to be 2 to power 40 into 5 to power 30. All of you know all of this, isn't it? That's going to be the HCF of these two numbers, right? Now, number of numbers that are divisible by, that divide both A and B, would be the number of divisors of the GCD of A and B. Number of numbers that divide both A and B, number of numbers that divide both A and B would be the number of divisors of their GCD. Yes or no? Number of numbers dividing A and B is the number of divisors of C, which is GCD of A and B, which is number of numbers dividing both A and B, right? GCD of A and B. How many divisors of this? 41 into 31. How much is it? 1271. That means number of numbers that divide A or B, at least one of them, number of numbers that divide A or B from principle of inclusion exclusion would be NA plus NB minus N of A intersection B. NA plus NB, which is 1681 plus 1891 minus, how much does it turn out to be? 2301. Okay. These are the number of divisors dividing A or B. That means at least one of them. A or B means at least one of them.